Okay, so now what we're going to do is we're going to continue to build upon the principles we put in place already. And we're going to do that with discrete probability models. So first, let's review a bit about probability models in general. Okay, so let's see, we're on part 3 now. Discrete probability models. Okay, let's first start by recalling the definition of a probability measure. P on subsets of omega. Omega is the sample space, all possible outcomes. Subsets of omega are events that we're interested in. The probability measure is what assigns probability to every possible event. So I will be quite repetitive in repeating that over and over again because it's important to keep it straight. There are 3 properties that the probability measure satisfies. First is that it assigns probability 1 to the sample space. It assigns a non-zero value to every admissible event in omega. And finally, is that if we have disjoint subsets, a countable collection of disjoint subsets of omega. Then the probability of the countable union is the sum of the probabilities. Okay. So now I'm going to start with some simple rules of probability. We actually proved a few of these already. Excuse me. We actually proved a few of these already. Some simple rules of probability. Okay. First one is finite additivity. Okay, so finite additivity. There we go. So finite additivity says that if we have disjoint, a finite collection of what's going on? Finite collection of disjoint events then the probability of that disjoint union is the sum of the probabilities. Okay. Next is the rule of differences. Rule of differences says that if we have if A is a subset of B, both are a subset of omega, so they're events, then probability of B minus A is the probability of B minus the probability of A. Okay. Left this as an exercise last time, and I'm going to prove it this time. So it's a good idea to try to work this out on your own if you haven't already. And if you did, here's how to do it. So the first is essentially what we want to do is we want to always, in some ways, we want to rewrite everything in terms of a way that's going to allow us to apply these axioms. That's really kind of the trick as we continue to build upon. So what we have here is we have B. So let's draw a picture of what this looks like and how we might be able to make use of this. So we have B, which is, let's say, some event, some subset, and then A is a part of B. Okay, so this is B, and this is A. And what we care about, evidently, is we care about, geez, we care about, all right, we care about B minus A, the stuff that's in B that's not in A. Okay. So let's just color that in. And how am I going to express this as a function of just the probabilities of A and B? Okay. And the way we can do it is we can say, well, let's talk about B first. B is the disjoint union of, since A is a part of B, B can be written as, well, any set can be written as the disjoint union of its intersection with A complement and the intersection of B with A, right? Because A union A complement is A union A complement is everything, omega. Okay. Now, that is equal to B intersect A complement. That's actually just B minus A, as we'll see in a second. B intersect A. What is B intersect A? Well, A is a part of B. So B intersect A is just A, right? So A inside of B implies that B intersect A equals A. Okay. And then B intersect A complement by definition is just B minus A. And B minus A is disjoint. from A. We've already said this is disjoint union. This thing doesn't want to cooperate. All right. So then from there, finite additivity. What does finite additivity tell us? Which we just proved above. Finite additivity of P implies that the probability of B can be written as probability of B minus A plus the probability of A. And then we just rearrange, we bring probability of A to the other side and we get the result that we're talking about, okay? Corollary, we've mentioned this last time. P is an increasing function. What does that mean? That means that if A is a subset of B, then the probability of A is less than or equal to the probability of B. Killing me. I don't know why this pencil. Kind of funny, actually. All right. Intuitively, adding outcomes to an event can only make the event more probable. Okay. Next is the complementation rule. Complementation rule says that for every event, probability of A complement is 1 minus the probability of A. How do we prove that? We use the proof, we use the previous two, finite additivity plus rule of differences. What's A complement? What's a clever way to write A complement is just omega minus A. Right? Why is that? This box is omega. This circle is A. My patience with this pencil is. All right. Okay. So this is A. A complement is everything everything in omega that's not in A. Well, that's just omega minus A. Okay. So that's pretty nice. But what do we know about that? Well, we know from the previous, the rule of differences. That means what? That means that the probability of A complement is equal to probability of omega minus A. And of course, A is a subset of omega. So rule of differences says this is equal to probability of omega minus probability of A. Probability of omega by PM1, probability of omega is 1, so that's 1 minus probability of A. Okay. And then finally, inclusion-exclusion. Really, this is a special case of inclusion-exclusion. This is called De Morgan's. This is one of De Morgan's rules. What it says is A and B are subsets. Then probability of A union B equals probability of A plus probability of B minus probability of A intersect B. Okay. Let's first prove it intuitively. And then let's prove it formally. So we have A and B. Okay. A and B. We're interested in how am I gonna do this? All right, so how I'm going to do this is I'm going to say, all right, let's color this part this color. Whoa. This thing gets a little crazy on me. All right, let's try that again. All right, so what are we trying to think about here? Well, we have a potentially A union B does not say anything about whether or not A and B are disjoint. There's no assumptions about that. So we have to keep in mind that there might be overlap, right? And so when there might be overlap, we have to account for that overlap when we add up probabilities, right? So if there's overlap and I take probability of A plus probability of B, what's going to happen? And this is basically the answer, is what's going to happen is this part in blue that I'm coloring right now is going to get counted twice. Okay. So how do I do this? So think about it. Probability of A is equal to, in terms of colors, it's the probability of the pink region plus probability of the blue region. Probability of B is probability of the green region plus probability of the blue region. Okay. So if we add them up, well, and what? And probability of A union B is probability of three things, right? Because they're all non-overlapping. It's a disjoint. So it's a disjoint collection of probability of pink plus probability of green plus probability of blue. So put it all together is based on this probability of A plus probability of B, we get our pink, we get our green, but we have two blues. So we have to subtract off a blue. And the blue is the probability of A intersect B. So that's a visual way of proving this. Okay. And how do we formalize this? Because that's not really a mathematical proof, but it's pretty good as an intuitive proof. Well, what we're going to do is we're just going to try to turn this intuition into math. How do we turn this intuition into math? Well, what did we do with these colors, right? We said that A union B can actually be written as A as the part of A not in B. I'm going to do it. Well, it's A union B minus A. But it's actually B minus A intersect B. Right? Because A contains the pink and the blue, and then B, the rest, the green part is B minus the part that the overlap. B minus A intersect B. Because A intersect B is a subset of B. So this is disjoint. And the fact that it's disjoint means that the probability of A union B is the probability of A plus probability of B minus A intersect B. Probability of B minus A intersect B, because A intersect B is a subset of B. Rule of differences is that this is probability of B minus probability of A intersect B. Those parentheses are extraneous. We don't need them. We'll get rid of them. And we have the inclusion-exclusion rule. Notice, so we're using finite additivity and the law of differences to get that. Note that in the special case, so note that first of all, probability of A union B does not equal probability of A plus probability of B. Common mistake. It's true only when probability of A intersect B equals 0, because we'd be subtracting off 0 and we would just be left with probability of A plus probability of B. So important to keep that in mind. Next thing we're going to do is we're going to go through a few examples in a little bit more depth, see how we can apply these rules.